All right, let's jump right in. If you're putting together a presentation for, say, a college engineering project, then you've come to the perfect place. Today, we're going to break down an absolute icon of industrial design, a really foundational piece of thermal engineering, the Babcock and Wilcox Boiler. Let's pull up the blueprint. Okay, so first things first, here is the full-on official textbook definition. Get ready for this. It's a horizontal drum axis, natural draft, natural circulation, multi-tubular, stationary, high-pressure water tube boiler.
Yeah, that is a mouthful, isn't it? It sounds incredibly complicated, but the real genius of this whole design is how simple it is once you really get the core idea. So let's break all that jargon down, piece by piece.
So let's just cut through all that noise. If you're going to remember just one thing from that super long definition, make it this. It's a water tube boiler. That's it. All it means is the water is inside a bunch of tubes, and the crazy hot furnace gases flow around the outside of them to heat it up. That single design choice, it's the key to absolutely everything that makes this thing tick.
This isn't some brand new technology. This design was patented way back in 1867 by George Babcock and Stephen Wilcox. But what's really incredible is its staying power. The core principles of their design are still absolutely essential today in thermal power plants all across the globe, generating the electricity that, powers our lives.
Okay, so to really understand how it all works, we've got to look at its anatomy. First up, the water and steam circuit.
Let's look at how these parts all dance together. At the very top, you have this big horizontal steam and water drum. Just think of it as a reservoir. It's half water, half steam. From there, the cooler water flows down through something called the downtake header into the many water tubes. And here's the really brilliant part. Those tubes are inclined at a very specific 15-degree angle. This allows the heated water and steam mixture to naturally rise up through the uptake header and go right back into the drum. That simple little tilt is what drives the entire circulation. No pumps needed. It's natural circulation in action. Pretty cool, right? All right, so that's the water circuit. Now let's talk about the other half of the equation, the furnace and all the accessories that actually create and direct all that heat. So below the water tubes is the furnace and grate, and that's where the magic, or I guess the fire, happens. Now, a less efficient design might just let all that hot gas shoot straight up and out the chimney. But here, the designers use these really clever fire brick walls called baffles. What they do is force the hot gases to travel in a zigzag path up and down across the tubes multiple times. This maximizes the contact time, squeezing every last possible bit of energy into the water. Finally, the steam from the drum gets one last blast of heat in the superheater, which makes it extra hot and dry for maximum power. So we've seen all the parts. Now let's put them in motion and really see this machine come to life. Let's trace the path of a single drop of water as it becomes powerful, superheated steam. The whole thing works because of that simple principle of natural circulation. It's kind of like a pot of boiling water, but just on a massive industrial scale. It's this continuous, self-sustaining loop that's powered by basic physics. Cooler, denser water naturally sinks from the drum down into the tubes. Then, as the furnace gases heat those tubes, the water inside gets hot, becomes way less dense, and naturally rises back up into the drum. Up there, the steam separates from the water, collects at the top, and gets sent over to the superheater for one last temperature boost. It's simple, it's elegant, and is incredibly effective. And really, it all comes back to this one number, that simple 15-degree incline. It seems like such a minor detail, but it is the secret sauce. It's what enables the entire process of natural circulation. Without that specific angle, the density difference between the hot and cold water just wouldn't be enough to drive the flow. A simple geometric choice powers the entire system.
Okay, so any good engineering analysis goes beyond just how something works to actually evaluate its design. So for your project, let's get to the final verdict, weighing the pros and cons of the Babcock and Wilcox boiler. So on the plus side, its design is super efficient, and it can generate steam really fast, which makes it great for fluctuating power demands. And since it's made of all these individual tubes, it's also way easier to repair. You can just replace one bad tube instead of the whole shebang. Plus, and this is a big one, it's a much safer design. If a tube fails, the damage is contained, which prevents the kind of catastrophic explosion that was possible with older boiler types. But what's the trade-off for all that performance? Well, it's high maintenance. It demands extremely pure water, because any little impurity can build up as scale and cause a tube to overheat and burst.
That means high costs for water treatment and cleaning, and it absolutely needs a continuous, reliable water supply.
So what's the big takeaway here? It's pretty amazing, really. This is a 19th century design that fundamentally still powers the 21st century. Its principles of efficient heat transfer and natural circulation are so solid, so robust, that they've stood the test of time, becoming a cornerstone of modern power generation.
And that leaves us with a final thought to chew on. This boiler's design is over 150 years old, yet its core principles are still generating our electricity today. It kind of makes you wonder, what design from our time, a piece of software, a device, maybe even just an idea, is so fundamentally sound that people will still be relying on it 150 years